In the soft light of dawn, as the sun rises over the Giza Plateau, shadows dance across limestone blocks that have stood silent for over 4,500 years. The Great Pyramid emerges from the desert like a mathematical theorem carved in stone, its edges sharp against the endless sky. This monument, built for the pharaoh Khufu around 2560 BC, represents far more than ancient ambition or royal vanity. It stands as perhaps the most remarkable mathematical achievement of the ancient world, a testament to minds that could envision perfection and then build it block by block. Picture yourself standing at the base of this colossal structure, your feet planted on limestone pavement that once gleamed white as fresh snow. Craning your neck to glimpse the pyramid's apex nearly 150 meters above, you begin to comprehend the audacity of this undertaking. Each side of the pyramid's base stretches approximately 230 meters, creating a square foundation so precise that the longest side differs from the shortest by less than 2 centimeters. To put this extraordinary accuracy in perspective, imagine trying to draw a perfect square on a football field, then expanding that square to cover 9 football fields arranged in a grid, all while maintaining that same level of geometric perfection. The margin of error would be smaller than the width of your thumb. The ancient Egyptians accomplished this feat using tools we might consider laughably primitive by modern standards. No laser levels guided their work, no computer calculations verified their measurements, no satellite positioning systems confirmed their alignments. Yet their precision rivals and sometimes exceeds what we achieve today with our most sophisticated electronic instruments. This suggests something profound about the mathematical knowledge embedded in their culture, a deep understanding of numerical relationships that went far beyond simple counting and basic arithmetic. The numbers themselves whisper secrets across millennia, each measurement a clue to the mathematical thinking that shaped this wonder. The pyramid's original height of 146.6 meters, combined with its base dimensions, creates ratios that have fascinated mathematicians and mystics for centuries. When you walk around the pyramid's perimeter, traversing the full circuit of its base, you cover a distance remarkably close to the circumference of a circle whose radius equals the pyramid's height. This relationship suggests the ancient builders understood profound mathematical concepts about the relationship between straight lines and curves, between earthbound geometry and the cosmic circles traced by celestial bodies. Consider the implications of this dimensional relationship. If you were to take the pyramid's height and use it as the radius of a circle, then calculate that circle's circumference, you would arrive at a number within a few meters of the pyramid's actual perimeter. This cannot be coincidence. It represents intentional mathematical design, a conscious decision to encode geometric relationships into the monument's fundamental proportions. The builders were creating not just a tomb or a symbol of power, but a three-dimensional expression of mathematical truth. Each block tells part of this extraordinary story. The average limestone block weighs about 2.5 tons, roughly equivalent to a modern automobile, yet some granite blocks in the king's chamber exceed 15 tons, matching the weight of several elephants. Multiply 2.3 million blocks by their average weight, and you arrive at a structure containing approximately 6 million tons of precisely cut and positioned stone. To transport this material using the wooden sledges, copper tools, and human labor available to the ancient Egyptians would require logistical planning of staggering complexity. The mathematical precision required to organize, transport, and place this material challenges our most basic assumptions about ancient capabilities. Each stone had to be quarried to specific dimensions, shaped to fit its designated position, transported across distances that sometimes exceeded hundreds of kilometers, and then lifted into place with tolerances measured in millimeters. The organizational mathematics alone boggle the modern mind. How do you coordinate the work of thousands of laborers, hundreds of skilled craftsmen, and dozens of specialized teams across a construction timeline spanning decades? But numbers and logistics alone cannot capture the pyramid's true marvel. Step inside this ancient wonder, and you begin to understand how mathematical concepts became physical reality. The entrance passage descends at exactly 26 degrees, an angle that appears throughout Egyptian architecture and seems related to astronomical observations. Walk through the ascending passage, and you encounter the same precise angle, but now climbing toward the heart of the pyramid. Every measurement reflects calculated decisions, not arbitrary choices. Stand inside the Grand Gallery, that soaring corridor that rises toward the King's Chamber, and you experience mathematical concepts made tangible in stone. The gallery rises at exactly 26 degrees, its corbelled ceiling distributing the immense weight of the pyramid through geometric principles still used in modern architecture. The precision of this construction astounds engineers today. The gallery's walls lean inward as they rise, each stone course positioned to transfer load efficiently while creating a space of breathtaking beauty. The mathematics of structural engineering, understood intuitively by ancient builders, enabled them to create spaces within their pyramid that have survived earthquakes, floods, and the passage of nearly 5 millennia. Every angle, every proportion, every measurement in the pyramid reflects calculated decisions made by minds that understood not just arithmetic, but the deeper relationships between numbers and physical reality. The pyramid chamber system demonstrates sophisticated understanding of three-dimensional geometry. The King's Chamber sits precisely at the pyramid's center of mass, positioned where structural forces balance most efficiently. The Queen's Chamber, despite its misleading name, occupies a position that relates mathematically to the pyramid's overall proportions. The pyramid's orientation reveals yet another layer of mathematical sophistication that continues to amaze astronomers and surveyors. Its four sides align with the cardinal directions to within 3 arc minutes of perfect accuracy. In practical terms, this means the ancient surveyors achieved precision equivalent to pointing a telescope at a distant star and being off by less than the width of a human hair held at arm's length. Such accuracy requires not just skilled craftsmanship and careful observation, but profound mathematical knowledge applied on a massive scale across irregular desert terrain. How did they achieve this remarkable precision? The answer lies in mathematical methods that combined astronomical observation with geometric calculation. The builders likely used the stars themselves as their compass, tracking the circumpolar stars that never set below the horizon. By observing these stars over time and applying geometric principles, they could establish true north with extraordinary accuracy. This process required mathematical thinking that bridged earthbound surveying problems with celestial mechanics. As shadows lengthen across the Giza plateau each day, the pyramid transforms from a simple geometric shape into something far more mysterious and compelling. The interplay of light and shadow creates patterns that change throughout the day, revealing the builder's understanding of solar geometry. During equinoxes, when day and night balance equally, the pyramid's shadow exhibits peculiar behaviors that suggest the ancient Egyptians incorporated sophisticated astronomical calculations into their architectural planning. Watch the pyramid at sunset, and you witness mathematical relationships playing out in real time. The structure's geometry interacts with the sun's changing position to create shadow patterns that would have held deep significance for the ancient Egyptians. These shadow phenomena demonstrate that the builders understood not just static geometry, but the dynamic relationships between their monument and the moving cosmos. The Great Pyramid stands not merely as a tomb or monument to royal power, but as a three-dimensional textbook of ancient mathematics. Its builders solved problems of surveying, engineering, and construction that would challenge modern professionals equipped with computers, laser instruments, and advanced materials. They calculated volumes for millions of stone blocks, managed logistics for a workforce that may have numbered in the tens of thousands, and maintained geometric precision across a construction project that likely lasted over 20 years. Each decision, from the pyramid's fundamental proportions to the placement of internal chambers and passages, reflects mathematical thinking of extraordinary sophistication. The builders understood principles of structural engineering that would not be formally codified until thousands of years later. They applied geometric relationships that modern mathematicians continue to study and debate. They achieved precision in surveying and construction that impresses today's experts. Walking away from the pyramid as evening approaches, your mind filled with wonder at this ancient achievement, you carry with you questions that bridge the ancient and modern worlds. How did a civilization without modern tools, without written equations as we understand them, without formal mathematical notation, achieve such stunning precision? What knowledge systems supported their remarkable calculations? How did they train the minds capable of conceiving and executing such an ambitious mathematical undertaking? The answers to these questions lie not in the pyramid alone, magnificent though it is, but in understanding the mathematical culture that conceived and built it. To truly comprehend this monument's significance, we must journey into the world of Egyptian numbers, exploring how ancient mathematicians thought, calculated, and solved problems that seem daunting even today. We must understand their number system, their methods of calculation, their approaches to geometry and measurement. The pyramid stands as their greatest theorem, proven not with symbols written on papyrus, but with limestone blocks arranged according to mathematical principles that continue to inspire wonder 4.5 millennia after their creators first gazed upon their completed masterpiece. It represents the culmination of a mathematical tradition that began in the Nile Valley thousands of years before Khufu's reign, a tradition of numerical thinking that would influence civilizations across the ancient world and lay foundations for mathematical knowledge that endures to this day. Long before the pyramids rose from the desert sands, the ancient Egyptians had already developed one of humanity's most elegant and enduring mathematical traditions. In the quiet halls of temples and the bustling workshops of scribes, a sophisticated understanding of numbers flourished along the banks of the Nile. This numerical wisdom, preserved in hieroglyphs carved on temple walls and inscribed on precious papyrus scrolls, reveals minds capable of remarkable mathematical thinking. The Egyptian number system possessed a beautiful simplicity that masked profound sophistication. Unlike our modern decimal system with its abstract place values, Egyptian numerals were direct and visual, each symbol representing a concrete quantity that could be grasped immediately by the human mind. A single vertical stroke represented 1 as natural and intuitive as holding up a finger. 10 appeared as an elegant arch, perhaps inspired by the shape of a hobble used to tie cattle legs, while 100 took the form of a coiled rope, and 1000 became a lotus flower, that sacred bloom that emerged from the Nile's muddy waters to reach toward the sun. Picture an ancient scribe sitting cross-legged in the shade of a temple portico, his reed pen moving gracefully across papyrus as he records the harvest yields of vast agricultural estates. To write the number 3427, he would carefully draw 3 lotus flowers for the thousands, 4 coiled ropes for the hundreds, 2 arches for the tens, and 7 vertical strokes for the units. The number emerged on papyrus as a series of recognizable symbols, each carrying its own weight and meaning, creating a mathematical notation that remained readable and comprehensible across centuries. This additive system, where larger numbers were built by combining symbols, required no understanding of place value or abstract positioning. A child could learn to read Egyptian numerals by simply counting symbols, yet the system proved remarkably powerful in the hands of skilled mathematicians. The largest number explicitly represented in Egyptian mathematics was 1 million, depicted by a human figure with arms raised toward the heavens in an expression of wonder or worship, as if acknowledging that such vast quantities approached the realm of the divine. But the true genius of Egyptian mathematics revealed itself in their treatment of fractions, those troublesome parts of wholes that challenge mathematical thinking even today. The Egyptians approached fractions with characteristic elegance and surprising restrictions. They worked almost exclusively with unit fractions, those simple expressions where one is divided by various whole numbers. 1/2, 1/3, 1/4, 1/5. These became the building blocks of Egyptian fractional mathematics, each represented by placing the symbol for 1 over the hieroglyph for the denominator. This seemingly limiting approach to fractions actually demonstrated profound mathematical insight. Any fraction, no matter how complex, could be expressed as the sum of different unit fractions. The fraction 2/5, for example, became 1/3 plus 1/15, a decomposition that required mathematical thinking of considerable sophistication. Egyptian mathematicians developed extensive tables showing how to break down complex fractions into sums of unit fractions, creating reference works that scribes consulted for centuries. The famous Rhind mathematical papyrus, dating to approximately 1650 BC, preserves one of the most complete records of Egyptian mathematical thinking. This remarkable document, over 5 meters long and inscribed with 87 mathematical problems, offers us a window into the minds of ancient mathematicians. The scribe Ahmes, who copied this papyrus from an even older source, described his work as giving exact reckoning for inquiring into all things, knowledge of all things mysterious, all secrets. Within the Rind papyrus, we discover problems that reveal the practical nature of Egyptian mathematics. How do you divide 7 loaves of bread among 10 men so that each receives an equal share? The answer requires understanding that 7/10 equals 2/3 plus 1/30, a decomposition that demonstrates sophisticated fractional arithmetic. Another problem asks how to calculate the area of a circular field with a diameter of 9 units, leading to approximations of that mysterious quantity we now call pi. The Egyptian approach to calculating the area of a circle reveals mathematical thinking that was both practical and surprisingly accurate. Rather than working with the true value of pi, which would not be precisely calculated for many centuries, Egyptian mathematicians used a practical approximation. They treated a circle as equivalent to a square whose side length was 8/9 of the circle's diameter. This method, while not perfectly accurate, gave results within 1% of the true area, more than sufficient for practical purposes like calculating field areas or planning construction projects. Egyptian scribes developed ingenious methods for multiplication and division that worked within their additive number system. To multiply, they used a process called doubling, repeatedly multiplying numbers by 2 and then adding the appropriate results. To calculate 13 times 21, for example, a scribe would first write out the doubles of 21. 1 times 21 equals 21, 2 times 21 equals 42, 4 times 21 equals 84, 8 times 21 equals 168. Since 13 equals 8 plus 4 plus 1, the final answer becomes 168 plus 84 plus 21, which equals 273. This doubling method, while seemingly cumbersome to modern eyes, actually proved remarkably efficient and virtually error-free. It required only the ability to double numbers and add, skills that any competent scribe could master. Moreover, the method worked equally well for fractions, allowing Egyptian mathematicians to perform complex calculations involving mixed numbers with confidence and accuracy. Division followed similar principles, but in reverse. To divide by a number, Egyptian mathematicians would find combinations of doubles that would sum to the dividend, then add the corresponding quotient values. The process required logical thinking and careful organization, but it produced reliable results without requiring memorization of multiplication tables or understanding of abstract mathematical operations. The sophistication of Egyptian mathematical thinking becomes even more apparent when we examine their approach to geometric problems. The Moscow mathematical papyrus, dating to approximately 1900 BC, contains a problem that demonstrates understanding of three-dimensional geometry that would not be formally proven until much later in mathematical history. The problem asks for the volume of a truncated pyramid, a frustum, and provides the correct formula involving the sum of the areas of the top, bottom, and middle sections. Egyptian mathematicians understood that the area of a triangle could be calculated as half the product of base and height, a relationship they applied to surveying problems throughout the Nile Valley. They knew that the area of a rectangle was simply length times width, and they could calculate the volumes of various three-dimensional shapes including pyramids, cylinders, and complex granary structures. Their understanding of right triangles and perpendicular relationships proved essential for surveying and construction. While they may not have formulated the Pythagorean theorem in abstract terms, Egyptian mathematicians clearly understood the relationship between the sides of right triangles. They used knotted ropes with specific proportions to create perfect right angles, a technique that enabled them to lay out building foundations and field boundaries with remarkable precision. The famous 3-4-5 triangle, where a rope knotted to create sides of 3, 4, and 5 units will always form a right angle, was well known to Egyptian surveyors. This practical application of geometric principles allowed them to establish perpendicular lines across vast distances, a skill essential for projects like pyramid construction where precision was paramount. Egyptian mathematics also ventured into areas we might consider more abstract. Problems involving arithmetic progressions appear in various papyri, demonstrating understanding of sequences and series. They could solve problems involving unknown quantities, though they did not use algebraic notation as we understand it today. Instead, they worked with what they called the aha, literally meaning heap, to represent unknown values in mathematical problems. A typical aha problem might read, a heap and its seventh part become 19. What is the heap? This requires understanding that if we call the unknown heap x, then x plus x divided by 7 equals 19, leading to the solution that the heap equals 16 and 5/7. Such problems demonstrate sophisticated mathematical reasoning, even without formal algebraic notation. The religious and cultural significance of numbers permeated Egyptian mathematical thinking. Certain numbers held sacred meaning that influenced architectural and artistic proportions. The number 7 appeared frequently in religious contexts, while specific ratios governed the proportions of temple designs and the creation of royal statues. Mathematics was never purely abstract for the Egyptians. It remained always connected to practical applications and spiritual significance. Egyptian mathematical education took place primarily in temple schools and scribal training centers, where young men learned the skills necessary for administrative careers. The curriculum emphasized practical problem-solving over theoretical understanding, preparing students to manage estates, calculate taxes, plan construction projects, and maintain the complex bureaucracy that governed Egyptian society. Master scribes passed down mathematical knowledge through careful copying of ancient texts, preserving methods and problems that had proven useful for generations. This conservative approach ensured continuity of mathematical tradition while gradually incorporating new insights and techniques. The result was a mathematical culture that remained remarkably consistent over thousands of years while continuing to evolve and adapt. The influence of Egyptian mathematics extended far beyond the borders of the Pharaonic kingdom. Greek mathematicians, including the legendary Thales and Pythagoras, traveled to Egypt to study with temple priests and learn mathematical techniques that would later influence the development of Greek geometry. The Egyptian emphasis on practical problem-solving and geometric relationships laid groundwork for later mathematical achievements throughout the Mediterranean world. As we prepare to explore how this sophisticated mathematical knowledge was applied to geometric problems, we carry with us an appreciation for the elegance and power of Egyptian numerical thinking. Their base 10 system, their ingenious approach to fractions, their practical methods for calculation, and their integration of mathematics with daily life created a foundation that supported remarkable achievements in architecture, engineering, and astronomy. The numbers that flowed from Egyptian reed pens onto papyrus scrolls were never merely abstract symbols. They represented cattle counts and grain harvests, field areas and building heights, astronomical observations, and religious proportions. This practical grounding gave Egyptian mathematics a robustness and reliability that enabled achievements like the Great Pyramid, where mathematical precision had to be maintained across decades of construction involving thousands of workers and millions of stones. From the simple elegance of hieroglyphic numerals to the sophisticated decomposition of complex fractions, Egyptian mathematics reveals minds capable of both practical problem-solving and abstract mathematical thinking. These ancient mathematicians created tools and techniques that would influence human civilization for millennia, laying foundations for the geometric knowledge that would enable their greatest architectural achievements. In the centuries before the great Greek mathematician Euclid ever dreamed of writing his systematic treatise on geometry, Egyptian mathematicians were already solving complex problems involving shapes, areas, and volumes with remarkable skill and intuition. Along the fertile banks of the Nile, where annual floods reshaped the landscape and redefined property boundaries, the practical needs of civilization gave birth to geometric insights that would eventually influence mathematical thinking throughout the ancient world. Picture the scene each year as the Nile's waters receded, leaving behind rich, dark soil perfect for cultivation, but also washing away the carefully surveyed field boundaries that defined individual property holdings. Teams of skilled surveyors, known as rope stretchers for their primary tool of knotted measuring ropes, would emerge to re-establish these boundaries with mathematical precision. Their work required not just measurement skills, but deep understanding of geometric relationships that could restore order to a landscape transformed by nature's annual cycle. The rope stretchers carried with them coils of carefully measured rope, each knot placed at precise intervals that had been verified and re-verified by generations of master surveyors. These ropes became instruments of geometric precision, allowing the surveyors to create perfect squares, establish right angles, and calculate areas with accuracy that modern instruments can barely improve upon. The sight of these men stretching their ropes across muddy fields, their movements guided by mathematical principles passed down through centuries, represented one of humanity's earliest systematic applications of geometric knowledge. The geometric problems preserved in Egyptian papyri reveal mathematical thinking that was both practical and surprisingly sophisticated. Consider the challenge faced by ancient architects who needed to calculate the amount of stone required for a temple foundation. The foundation might be rectangular, but its dimensions could involve complex fractional measurements. Egyptian mathematicians developed reliable methods for calculating areas of rectangles and triangles, even when the measurements involved their beloved unit fractions. A typical problem from the mathematical papyri might ask for the area of a rectangular field measuring 12.5 cubits by 7 1/3 cubits. The solution required multiplying mixed numbers expressed as unit fractions, a calculation that demanded both computational skill and geometric understanding. The scribe would first convert the mixed numbers into sums of unit fractions, then apply multiplication techniques using the doubling method, finally arriving at an area expressed once again as a sum of unit fractions. The calculation of circular areas presented Egyptian mathematicians with one of their most intriguing challenges. Unlike rectangles and triangles, circles could not be easily broken down into simpler shapes using the geometric knowledge available to ancient mathematicians. Yet the need to calculate circular areas was constant, driven by practical problems involving circular granaries, round fields, and cylindrical containers for storing grain and other precious commodities. Egyptian mathematicians approached this challenge with characteristic ingenuity, developing an approximation method that was both practical and remarkably accurate. They observed that a circle could be approximated by a square whose side length was 8/9 of the circle's diameter. This relationship, while not perfectly precise, gave results accurate to within about 0.5% of the true area, more than sufficient for any practical application in the ancient world. This approximation method reveals sophisticated mathematical thinking that goes far beyond simple trial and error. The Egyptians essentially discovered that their method gave a value for pi of approximately 3.16, remarkably close to the true value of 3.14159. How did they arrive at this approximation? The answer likely involves geometric insights about the relationship between circles and polygons, perhaps developed through careful observation and measurement of actual circular objects. The Moscow Mathematical Papyrus preserves one of the most remarkable examples of Egyptian geometric sophistication in a problem that asks for the area of a curved surface. The problem describes what appears to be a basket or container with curved sides, and the solution demonstrates understanding of geometric relationships that would not be formally proven until much later in mathematical history. The Egyptian approach to this problem suggests familiarity with concepts that approach what we now call integral calculus. Egyptian mathematicians also grappled with three-dimensional geometric problems that required understanding of volume relationships. The calculation of pyramid volumes presented particular challenges because pyramids, unlike simple rectangular boxes, involve complex relationships between base area and height. Yet problems in the mathematical papyri show that Egyptian mathematicians understood the correct formula for pyramid volume, 1/3 of the base area multiplied by the height. This understanding of pyramid volumes was not merely theoretical, but had profound practical implications for the massive construction projects that defined Egyptian civilization. Calculating the volume of a planned pyramid allowed architects to estimate the quantity of stone that would need to be quarried and transported, a calculation essential for planning construction timelines and organizing the massive workforce required for such projects. The truncated pyramid, or frustum, presented an even more complex geometric challenge. The Moscow papyrus contains a famous problem asking for the volume of a frustum with a square base measuring 4 units on each side, a square top measuring 2 units on each side, and a height of 6 units. The solution provided in the papyrus gives the correct formula: height multiplied by 1/3 of the sum of the base area, top area, and the square root of their product. This formula for frustum volume represents mathematical thinking of extraordinary sophistication. The correct derivation of this formula requires understanding of geometric relationships that would challenge modern calculus students. Yet, Egyptian mathematicians, working without formal algebraic notation or systematic geometric proofs, somehow arrived at the correct answer. This achievement suggests geometric insights that we can barely comprehend today. The practical applications of Egyptian geometry extended far beyond architectural projects to encompass the entire fabric of ancient Egyptian society. Tax collectors used geometric calculations to determine the productive capacity of fields with irregular shapes. Military engineers applied geometric principles to design siege equipment and calculate trajectories for projectiles. Temple priests used geometric relationships in the design of sacred spaces, ensuring that religious buildings reflected divine proportions and cosmic harmonies. Egyptian surveyors developed sophisticated techniques for measuring distances across terrain that was often irregular and challenging. They understood how to use similar triangles to calculate heights of objects that could not be measured directly, such as tall buildings or the heights of cliffs along the Nile. This technique, which we now associate with trigonometry, allowed them to create accurate maps and plan construction projects across varied landscapes. The concept of similar triangles also enabled Egyptian mathematicians to solve problems involving proportional relationships. If a shadow of known length was cast by an object of known height, they could calculate the height of any other object by measuring its shadow and applying proportional reasoning. This technique proved invaluable for architectural planning, where scale models could be used to determine the dimensions of full-sized structures. Egyptian geometric thinking also embraced what we might consider more abstract concepts. They understood that the angles in a triangle sum to a fixed total, though they expressed this relationship in practical rather than theoretical terms. They knew that certain combinations of lengths would always produce right triangles, and they used this knowledge to create perpendicular lines with remarkable precision. The famous 3-4-5 triangle was just one example of Egyptian familiarity with what we now call Pythagorean triples. They also knew that triangles with sides in the ratios 5-12-13 and 8-15-17 would always contain right angles. This knowledge, preserved in their rope stretching techniques, allowed surveyors to establish perfect right angles across vast distances using only measured ropes and careful positioning. Egyptian mathematicians also explored geometric progressions and sequences, though their approach remained firmly grounded in practical applications. They understood how areas scaled when linear dimensions were multiplied by constant factors, knowledge essential for enlarging architectural plans or calculating material requirements for projects of different sizes. If you doubled the dimensions of a square foundation, the area would increase by a factor of 4, and the volume of any structure built upon it would increase by a factor of 8. The preservation of Egyptian geometric knowledge depended largely on the scribal tradition that maintained mathematical texts across centuries. Master scribes carefully copied ancient problems and solutions, sometimes adding commentary or additional examples based on their own experience. This process of preservation and transmission ensured that geometric insights developed over many generations remained available to later mathematicians and engineers. The influence of Egyptian geometry extended throughout the ancient Mediterranean world as scholars from other civilizations traveled to Egypt to study with temple priests and master mathematicians. Greek mathematicians, including Thales and Pythagoras, acknowledged their debt to Egyptian geometric knowledge. The systematic approach to geometry that would later characterize Greek mathematics built upon foundations laid by Egyptian mathematicians working centuries earlier. Yet Egyptian geometry remained fundamentally different from the abstract proof-based approach that would later develop in Greece. Egyptian mathematicians focused on solving practical problems rather than proving general theorems. Their geometric knowledge was embedded in specific examples and applications rather than expressed as universal principles. This practical orientation gave Egyptian geometry a robustness and reliability that served their civilization well for thousands of years. The geometric principles discovered and applied by Egyptian mathematicians were not abstract curiosities, but essential tools for maintaining one of history's most successful civilizations. From the annual resurveying of flood-damaged fields to the planning of monuments that would endure for millennia, geometric knowledge provided the mathematical foundation for Egyptian achievements in engineering, architecture, and administration. As we prepare to explore how these geometric principles were applied to create the perfect proportions of the pyramids, we carry with us an appreciation for the practical wisdom and mathematical insight of ancient Egyptian mathematicians. Their geometric knowledge, developed through centuries of careful observation and practical application, created tools and techniques that would enable architectural achievements of breathtaking precision and enduring beauty. The transition from abstract geometric knowledge to its application in monumental architecture represents one of the most remarkable achievements in the history of mathematics. Egyptian mathematicians had developed the tools. Now master builders would use those tools to create structures that would amaze and inspire humanity for thousands of years to come. The geometry that emerged from practical problems of field measurement and construction planning would soon be embodied in limestone and granite, creating monuments that stand as eternal testimonies to the power of mathematical thinking. Standing in the shadow of the Great Pyramid as the afternoon sun traces its ancient path across the sky, you begin to sense that this monument embodies mathematical relationships that transcend mere engineering necessity. The pyramid's proportions speak in the language of numbers, revealing ratios and relationships that have captivated mathematicians, architects, and mystics for over 4 millennia. These are not arbitrary dimensions chosen for convenience or construction ease, but carefully calculated proportions that encode profound mathematical truths in stone. The fundamental ratio that defines the Great Pyramid's character lies in the relationship between its height and the distance from the center of its base to the midpoint of any side. This crucial measurement, known as the apothegm, creates a slope ratio that Egyptian architects expressed as 14:11. In modern terms, this translates to a slope angle of approximately 51.84 degrees, a precise inclination that gives the pyramid its distinctive silhouette and creates mathematical relationships that continue to amaze scholars today. To understand the significance of this 14:11 ratio, imagine standing at the pyramid's base and looking up along one of its faces toward the apex. The steepness you observe, that perfect balance between dramatic ascent and structural stability, results from mathematical calculations that took into account not only aesthetic considerations, but also the complex engineering requirements of building with limestone blocks weighing several tons each. Too steep, and the structure would be unstable; too shallow, and it would lack the impressive height that proclaimed pharaonic power across the landscape. The 14:11 ratio appears throughout Egyptian architecture, suggesting that it held special significance in their mathematical and possibly religious thinking. This proportion creates what mathematicians call the encodes, an Egyptian unit of measurement that expressed slope as the horizontal distance corresponding to each unit of vertical rise. For the Great Pyramid, the encodes equals 5 1/4 palms per cubit of height, a relationship that allowed Egyptian architects to maintain consistent angles across the entire structure while working with their traditional units of measurement. But the mathematical relationships embedded in the Great Pyramid extend far beyond simple slope calculations. When you walk completely around the pyramid's base, measuring each step carefully, you discover that the perimeter of the base relates remarkably to the pyramid's height in a way that echoes one of mathematics' most fundamental constants. The ratio of the pyramid's perimeter to its height approximates 2 times pi, that mysterious number that relates the circumference of any circle to its diameter. This relationship suggests something profound about the mathematical thinking that guided the pyramid's design. If you were to construct a circle using the pyramid's height as the radius, the circumference of that circle would closely match the perimeter of the pyramid's square base. This cannot be coincidence. The ancient architects deliberately encoded this circular relationship into their square-based structure, creating a monument that bridges the geometry of straight lines and curves in stone. The implications of this perimeter to height relationship have sparked debates among mathematicians and historians for centuries. Did the ancient Egyptians consciously design their pyramid to embody the value of pi, that transcendental number whose decimal expansion never repeats and never ends? Or did this relationship emerge naturally from other design considerations, perhaps related to the practical requirements of construction or the symbolic meaning they attach to certain proportions? The answer may lie in understanding how Egyptian mathematicians approached the concept we now call pi. As we explored in earlier chapters, they used an approximation of 3.16 for calculating circular areas, remarkably close to the true value of pi. If they applied this same approximation to the pyramid's design, the resulting perimeter-to-height ratio would closely match what we observe in the actual structure. This suggests intentional mathematical design rather than accidental approximation. Consider another fascinating numerical relationship hidden within the pyramid's dimensions. The ratio of the pyramid's height to half its base length equals approximately 1.27, a number that closely approximates 4 divided by pi. This relationship creates yet another connection between the pyramid's geometry and fundamental mathematical constants, reinforcing the impression that the ancient architects were encoding sophisticated mathematical knowledge into their monument's proportions. The debate over whether the golden ratio, that special number approximately equal to 1.618, appears in the pyramid's design has raged for decades among mathematicians and archaeologists. Some researchers claim to find the golden ratio in various proportional relationships within the pyramid, while others argue that these discoveries result from selective measurement and wishful thinking. The truth likely lies somewhere between these extremes, acknowledging both the mathematical sophistication of the pyramid's designers and the human tendency to find meaningful patterns in numerical relationships. What we can say with certainty is that the pyramid's proportions create a sense of visual harmony that has impressed observers for millennia. Whether this harmony results from deliberate application of mathematical ratios like the golden ratio or from other design principles, the psychological and aesthetic impact remains undeniable. The pyramid's proportions feel right to human perception, creating a sense of balance and completeness that transcends cultural and historical boundaries. The mathematical relationships within the Great Pyramid become even more intriguing when we examine the dimensions of its internal chambers and passages. The King's Chamber, that granite sanctuary at the pyramid's heart, displays proportional relationships that echo those of the overall structure. The chamber's length, width, and height relate to each other in ratios that some researchers claim reflect mathematical constants, though the evidence for such relationships remains debated among scholars. The Grand Gallery, that soaring passage that leads to the King's Chamber, demonstrates mathematical precision in its construction that amazes modern engineers. The gallery's length relates to its height in proportions that may reflect astronomical considerations, as the passage aligns with certain stellar observations that were important to ancient Egyptian religious beliefs. The corbelled ceiling of the gallery distributes structural loads through geometric principles that require sophisticated understanding of mathematical relationships in three-dimensional space. Even the pyramid's entrance passage, descending into the bedrock at its precise 26-degree angle, reflects mathematical considerations that go beyond simple structural requirements. This angle appears frequently in Egyptian architecture and may relate to astronomical observations of circumpolar stars. The mathematical consistency of this angle across multiple pyramid complexes suggests that it held special significance in Egyptian architectural and possibly religious thinking. The relationship between the Great Pyramid's dimensions and various systems of ancient measurement has provided another avenue for mathematical exploration. Some researchers have proposed that the pyramid's proportions encode relationships between different units of measurement, creating a three-dimensional reference standard that preserved important mathematical and metrological information for future generations. While such theories remain speculative, they highlight the potential for mathematical information to be embedded in architectural proportions. The precision with which these proportional relationships were achieved in the actual construction continues to amaze modern engineers and mathematicians. Building a structure with a base covering over 13 acres while maintaining mathematical ratios accurate to fractions of a percent requires not only sophisticated mathematical knowledge, but also extraordinary skill in surveying, construction management, and quality control. The ancient builders had to translate abstract mathematical relationships into physical reality using tools and techniques that seem primitive by modern standards. The mathematical analysis of the Great Pyramid has been complicated by the effects of time and human intervention on the structure's original dimensions. The pyramid has lost its smooth outer casing stones, reducing its height by several meters and making precise measurement of its original proportions challenging. Earthquakes, thermal expansion and contraction, and the gradual settling of the massive structure have all introduced small changes to its dimensions over the millennia. Despite these challenges, careful measurement and analysis have revealed that the pyramid's original proportions were executed with remarkable precision. The base is square to within a few centimeters across its 230-meter width, and the slope angles of the four faces match each other to within minutes of arc. Such precision in a structure of this scale represents one of the greatest achievements in the history of construction and applied mathematics. The influence of the Great Pyramid's proportional relationships extended throughout Egyptian architecture and beyond. Later pyramids often echoed similar mathematical relationships, though none matched the Great Pyramid's precision and scale. The mathematical principles embodied in the pyramid's design influenced architectural traditions that spread throughout the ancient Mediterranean world, carrying Egyptian mathematical knowledge to civilizations that would build upon these foundations. Modern computer analysis has enabled researchers to explore the pyramid's mathematical relationships with unprecedented precision and detail. Digital models can test various theories about the pyramid's proportional relationships, examining how small changes in dimensions might affect the mathematical constants that appear to be encoded in the structure. These analyses have both confirmed some long-held theories and challenged others, contributing to our evolving understanding of ancient mathematical knowledge. The psychological impact of the pyramid's proportions on human observers provides another dimension for mathematical analysis. Research in environmental psychology and neuroaesthetics has begun to explore how certain mathematical relationships in architectural proportions affect human perception and emotional response. The pyramid's enduring ability to inspire awe and wonder may result partly from mathematical relationships that resonate with deep patterns in human cognition and perception. The Great Pyramid stands as perhaps the most remarkable example of mathematical knowledge made manifest in physical form. Its proportions encode relationships between fundamental mathematical constants. Its construction required solving complex problems in applied mathematics, and its enduring presence continues to inspire mathematical investigation and wonder. Whether its builders consciously intended to create a monument to mathematical knowledge or whether these relationships emerged from other design considerations, the pyramid remains a testament to the power of mathematical thinking to create beauty, meaning, and permanence. As we prepare to explore how the ancient Egyptians achieved the remarkable precision necessary to realize these mathematical relationships in actual construction, we carry with us an appreciation for the sophistication and intentionality that guided the pyramid's design. The transition from mathematical conception to physical reality required solving problems in surveying, logistics, and construction management that challenged the limits of ancient technology and organizational capability. The perfect proportions we admire today resulted from mathematical knowledge applied with extraordinary skill and determination across decades of monumental construction effort. In the pre-dawn darkness of the Giza Plateau, nearly 5,000 years ago, a master surveyor stood motionless beneath a canopy of stars, his eyes fixed on the celestial pole around which the heavens slowly wheeled. The desert air was still and clear, offering perfect conditions for the precise astronomical observations that would guide one of history's most ambitious mathematical undertakings. This surveyor and his team faced a challenge that would test the limits of ancient mathematical knowledge, establishing a perfectly square foundation covering over 13 acres with an accuracy that would impress modern engineers equipped with laser instruments and satellite positioning systems. The task before these ancient mathematicians was staggering in its complexity and precision requirements. They needed to mark out a square base measuring 230 meters on each side, oriented precisely to the cardinal directions, on irregular desert terrain that sloped and undulated across the construction site. Every measurement had to be perfect, every angle exactly 90 degrees, every side precisely parallel to its opposite. The smallest error would compound across the massive structure, potentially causing catastrophic structural problems or creating a monument that failed to embody the mathematical perfection that Egyptian religious and architectural traditions demanded. The foundation of this extraordinary precision lay in the ancient Egyptians' sophisticated understanding of astronomical mathematics. The surveyor beneath the stars was applying knowledge that had been developed and refined over centuries of careful observation, using the eternal movements of celestial bodies to establish fixed reference points on the ever-changing Earth. The technique centered on observations of circumpolar stars, those bright points of light that never disappeared below the horizon but instead traced endless circles around the celestial pole. Picture the patient dedication required for this astronomical surveying method. Night after night, the master surveyor would observe the movement of selected stars, carefully noting their positions relative to a precisely vertical plumb line. Using a simple but ingenious instrument consisting of a straight staff with a plumb bob hanging from a crossbar, he could track the apparent movement of stars across the sky with remarkable precision. When a circumpolar star reached its highest point in its circular path, it marked true north with an accuracy that modern instruments struggle to improve upon. The mathematics underlying this stellar surveying technique reveals the sophisticated astronomical knowledge that Egyptian mathematicians possessed. They understood that the apparent movement of stars resulted from the Earth's rotation, though they conceptualized this in terms of the celestial sphere rotating around a stationary Earth. They knew that by observing the extreme positions of circumpolar stars, they could establish a north-south line accurate to within minutes of arc, a precision level that would ensure their pyramid's alignment met the most demanding standards. But establishing true north was only the beginning of the surveying challenge. The next phase required translating this single reference line into a perfect square foundation covering acres of irregular terrain. This task demanded not only astronomical knowledge but also sophisticated understanding of terrestrial geometry and practical surveying mathematics. The surveyors needed to create right angles with absolute precision, establish parallel lines across hundreds of meters, and ensure that all measurements remained accurate despite the challenges of working on uneven ground. The creation of perfect right angles relied on mathematical principles that the Egyptians had mastered through centuries of practical application. The famous 3-4-5 triangle, where sides in the ratio 3:4:5 always create a right angle, provided the foundation for their perpendicular line construction. Using carefully measured ropes with knots placed at precise intervals, surveyors could create right angles with remarkable accuracy by simply ensuring that their rope formed triangles with the correct proportional relationships. But the 3-4-5 triangle was just one of several Pythagorean relationships that Egyptian surveyors understood and applied. They also knew that triangles with sides in the ratios 5:12:13, 8:15:17, and 20:21:29 would always contain perfect right angles. This knowledge gave them multiple tools for creating and verifying perpendicular relationships, allowing them to cross-check their work and maintain accuracy across the vast scale of their project. The process of establishing the pyramid's baseline required mathematical techniques that bridged astronomical precision with terrestrial measurement. Starting from their astronomically determined north-south line, the surveyors would use rope and stake methods to establish the first side of their square foundation. This baseline had to be perfectly straight across its 230-meter length, a requirement that demanded sophisticated understanding of how to maintain linear accuracy across uneven terrain. Creating a straight line across irregular ground presents mathematical challenges that are not immediately obvious to modern observers accustomed to laser levels and electronic instruments. The ancient surveyors solved this problem using a technique based on geometric principles involving line-of-sight observations and triangulation methods. By establishing intermediate points along their intended baseline and carefully sighting along these points, they could ensure that their line remained straight despite hills, valleys, and other terrain irregularities. The mathematical precision required for this baseline establishment becomes clear when we consider the tolerances involved. An error of just 1 degree in the baseline's direction would cause the pyramid's opposite sides to be misaligned by over 4 meters. Such misalignment would be immediately obvious and would create structural problems that could compromise the entire monument. The surveyors had to maintain accuracy equivalent to pointing across 2.5 football fields and being off by less than the width of a pencil. Once the baseline was established, the surveyors faced the challenge of creating the remaining 3 sides of their square foundation. This required not only establishing perpendicular lines from the ends of their baseline, but also ensuring that these perpendicular lines extended to exactly the correct length, and that the 4th side connecting the ends of these perpendiculars was both parallel to the baseline and exactly the same length. The mathematical technique for establishing perpendicular lines at the ends of the baseline relied on the rope triangle methods that Egyptian surveyors had perfected. At each end of the baseline, they would carefully measure out ropes in the 3-4-5 ratio, ensuring that the resulting triangle created a perfect right angle. The perpendicular sides of their foundation square would then extend along the directions established by these rope triangles. Maintaining accurate measurements across the hundreds of meters required for each side of the foundation demanded mathematical understanding of how measurement errors could accumulate. The ancient surveyors developed techniques for subdividing their long measurements into shorter segments that could be measured more accurately, then combining these segments using mathematical principles that minimized cumulative error. This approach required understanding of what modern mathematicians call error propagation and measurement uncertainty. The verification that their foundation was indeed a perfect square required additional mathematical techniques that demonstrated the sophistication of Egyptian surveying knowledge. The surveyors would measure both diagonals of their square foundation, ensuring that these measurements were identical and that they related to the side length by the square root of 2. While they may not have expressed this relationship in modern algebraic terms, they clearly understood the geometric principle and could apply it to verify their work. The accuracy achieved by these ancient surveyors continues to amaze modern measurement specialists. The Great Pyramid's base is square to within 2 centimeters across its 230-meter width, representing a precision of better than 1 part in 10,000. The pyramid's orientation differs from true north by only 3 arc minutes, an accuracy that approaches the limits of what can be achieved using traditional surveying instruments even today. This extraordinary precision resulted not from advanced technology, but from mathematical knowledge applied with meticulous care and extraordinary skill. The ancient surveyors understood the geometric principles that governed their work. They had developed practical techniques for applying these principles accurately in the field, and they possessed the patience and dedication necessary to achieve mathematical perfection on a monumental scale. The surveying of the Great Pyramid's foundation also required sophisticated understanding of the mathematical relationships between their measuring units and the final dimensions they needed to achieve. The pyramid's designers had specified its dimensions in terms of Egyptian cubits, but the actual construction measurements needed to account for the specific proportional relationships that would create the desired slope angles and overall proportions. The mathematical conversion between design dimensions and construction measurements was complicated by the fact that Egyptian cubits varied slightly in different applications and locations. The surveyors needed to ensure that their foundation measurements were based on the specific cubit standard that would produce the exact proportional relationships required by the pyramid's mathematical design. This attention to metrological detail demonstrates the deep integration of mathematical thinking throughout the entire construction process. The environmental challenges of desert surveying added another layer of mathematical complexity to the project. The extreme temperature variations between day and night caused measuring ropes to expand and contract, potentially introducing errors into critical measurements. The surveyors had to understand these thermal effects and develop techniques for compensating for them, perhaps by conducting their most critical measurements at specific times of day when temperatures were most stable. Wind and sand presented additional challenges that required mathematical solutions. Strong winds could deflect plumb lines and interfere with astronomical observations, while blowing sand could obscure markers and reference points. The surveyors developed techniques for protecting their instruments and maintaining their reference systems despite these environmental challenges, demonstrating the practical application of mathematical knowledge under difficult field conditions. The achievement of the Giza surveyors influenced construction practices throughout the ancient world and established standards of precision that would be emulated but rarely equaled. Their mathematical techniques for astronomical surveying, perpendicular line establishment, and large-scale measurement were transmitted to other civilizations and adapted for different architectural and engineering projects. The legacy of their mathematical achievement extends far beyond the specific monument they created. The surveying techniques developed for the Great Pyramid demonstrated that mathematical knowledge could be applied to solve practical problems of extraordinary complexity and scale. Their work established precedents for precision and accuracy that would influence engineering and construction practices for thousands of years. As we prepare to explore how the mathematical precision achieved in surveying was translated into the massive logistical challenge of moving and placing millions of stone blocks, we carry with us an appreciation for the remarkable mathematical sophistication that guided every aspect of the pyramid's construction. The transition from precise foundation layout to actual building construction would require mathematical solutions to problems of transportation, lifting, and placement that tested the limits of ancient engineering knowledge and organizational capability. In the quarries along the Nile, the sound of copper chisels striking limestone created a rhythm that would echo for decades. Each strike represented not just physical labor but mathematical precision applied to one of history's most ambitious construction projects. The Great Pyramid would require approximately 2.3 million individual stone blocks, each weighing an average of 2.5 tons, all precisely shaped, transported, and positioned according to mathematical specifications that demanded perfection on an almost incomprehensible scale. Picture the mathematical challenge that faced the ancient project managers as they contemplated this monumental undertaking. 2.3 million blocks, each requiring individual attention from quarrying through final placement, spread across a construction timeline of approximately 20 years. This translates to roughly 300 blocks that needed to be quarried, shaped, transported, and precisely positioned every single day, working year-round without pause. The organizational mathematics alone would challenge modern project managers equipped with computers, sophisticated logistics software, and global supply chains. The volume calculations that governed the pyramid's construction reveal the staggering scale of material requirements. The completed pyramid contains approximately 2.6 million cubic meters of stone, representing roughly 6 million tons of precisely placed material. To put this in perspective, this amount of stone could build a wall 1 meter high and 1 meter thick, stretching from London to Rome. Yet every block in this vast quantity had to be positioned with mathematical precision measured in millimeters, creating a structure where individual stones fit together so perfectly that you cannot slip a knife blade between them. The mathematical principles governing stone cutting and shaping required understanding of three-dimensional geometry that was both practical and sophisticated. Each block had to be shaped not just to specific dimensions, but to precise angles that would ensure proper fit within the pyramid's complex geometry. Corner blocks needed compound angles that would maintain the pyramid's slope on two faces simultaneously. Blocks for the internal chambers required even more complex shaping to create the precise architectural forms that the pyramid's design demanded. Consider the mathematical challenge of cutting stones for the pyramid's sloping faces. Each face rises at approximately 51.84 degrees, requiring every block to be shaped with surfaces that precisely match this angle. The ancient stonecutters had to understand not just the overall slope angle, but how this angle translated into the specific cuts required for blocks of different sizes and positions within the structure. A block intended for the 20th course from the bottom would require different angled cuts than a block for the 50th course, even though both had to maintain the same overall slope relationship. The transportation of these massive blocks from quarries to construction site presented mathematical problems that required ingenious solutions. Most of the pyramid's limestone blocks came from quarries on the Giza plateau itself, but the finest quality limestone for the outer casing came from quarries at Tura across the Nile River. The granite blocks used in the king's chamber traveled even farther, quarried near Aswan, over 800 kilometers to the south. The mathematics of river transport during the annual Nile flood season required sophisticated understanding of buoyancy, load distribution, and navigation. The ancient engineers had to calculate the lifting capacity of their wooden barges, ensuring that heavily loaded vessels could navigate the shallow channels and shifting sandbars that characterized the flooded Nile. A typical granite block weighing 15 tons required a barge capable of carrying at least 20 tons of cargo while maintaining sufficient freeboard to navigate safely. The overland transport of stones from river landing sites to the pyramid construction area demanded mathematical solutions to problems of force friction and mechanical advantage. The most likely transport method involved wooden sledges pulled by teams of men, possibly assisted by cattle or other draft animals. The mathematical relationship between the force required to move a loaded sledge and factors like surface conditions, slope angles, and load distribution determined how many workers were needed for each transport operation. Experimental archaeology has provided insights into the mathematical principles that governed these transport operations. Modern researchers have demonstrated that a team of 20 men can move a 2.5-ton block on a wooden sledge across relatively smooth ground. Extrapolating from these experiments, the daily transport of 300 blocks would have required a workforce of approximately 6,000 men dedicated solely to moving stones from quarries to construction site, not including the additional workers needed for quarrying, shaping, and placement operations. The lifting and placement of stones within the growing pyramid structure presented perhaps the most complex mathematical challenges faced by the ancient builders. As the pyramid rose higher, each stone had to be lifted greater distances and positioned with increasing precision. The mathematical relationships governing mechanical advantage, force multiplication, and structural stability all came into play as the builders developed techniques for raising massive blocks to heights exceeding 140 meters. The debate over ancient lifting methods has generated numerous theories, each involving different mathematical principles and mechanical approaches. The straight ramp theory proposes that the Egyptians built a massive earthen ramp that rose alongside the pyramid, allowing workers to drag stones up an inclined plane to the required height. The mathematical analysis of this approach reveals both its potential advantages and significant problems. A straight ramp extending to the pyramid's full height would require a slope gentle enough for loaded sledges to navigate, probably no steeper than 7 to 8 degrees. Mathematical calculations show that such a ramp reaching the pyramid's apex would stretch over 1.5 kilometers from the pyramid's base, and would itself contain more material than the pyramid. This massive construction project within a construction project seems unlikely given the practical constraints faced by ancient builders. The spiral ramp theory offers a more mathematically elegant solution to the lifting problem. This approach envisions a ramp that winds around the pyramid's exterior as construction progresses, maintaining a manageable slope while requiring much less material than a straight ramp. The mathematical advantage of this design lies in its efficient use of space and materials, but it raises questions about how the pyramid's corner angles and edge alignments could be maintained with a ramp covering the exterior surfaces. Recent research has focused on internal ramp theories that propose lifting systems built within the pyramid itself. The mathematical appeal of this approach lies in its ability to solve the lifting problem without requiring massive external construction. Internal ramps could follow corridors and chambers within the pyramid, using the mathematical principle of mechanical advantage to lift stones efficiently while maintaining access to all parts of the structure under construction. The mathematics of internal ramp systems involves complex three-dimensional geometry and sophisticated understanding of load distribution. The ramps would need to spiral upward through the pyramid's interior, maintaining sufficient width for loaded sledges while not compromising the structural integrity of the surrounding stonework. The mathematical relationships governing the ramp's gradient, width, and structural support requirements would have challenged the most skilled ancient engineers. Regardless of which lifting method was actually employed, the placement of individual stones required mathematical precision that challenges modern understanding. Each block had to be positioned not just in the correct location horizontally, but also at precisely the right height to maintain the pyramid's geometric relationships. The mathematical tolerances involved become clear when we consider that the pyramid's faces must maintain their slope angle across hundreds of stone courses, with errors in individual block placement potentially compounding into major deviations from the intended geometry. The logistics of coordinating multiple work crews across the vast construction site required mathematical planning that encompassed every aspect of the building process. Quarrying teams, transport crews, stone shaping specialists, and placement workers all had to coordinate their efforts according to mathematical schedules that ensured steady progress without creating bottlenecks or shortages. The mathematical complexity of this coordination rivals that of modern industrial production systems. The quality control systems employed by ancient builders demonstrated sophisticated understanding of mathematical relationships in construction. Supervisors used measuring devices and geometric techniques to verify that each stone course maintained the correct height, slope angle, and alignment relationships. These verification procedures required mathematical knowledge that could detect small errors before they compounded into larger problems affecting the overall structure. The mathematical precision achieved in the pyramid's construction becomes even more remarkable when we consider the environmental challenges that workers faced. Temperature variations caused stones and measuring devices to expand and contract, potentially affecting the accuracy of placement operations. Wind could interfere with plumb line measurements and other precision tasks. The mathematical techniques employed had to account for these environmental factors while maintaining the exacting standards that the project demanded. The seasonal nature of much construction work added another layer of mathematical complexity to project planning. The annual Nile flood affected transportation schedules, quarrying operations, and workforce availability. Project managers had to develop mathematical models that could accommodate these seasonal variations while maintaining steady progress toward completion. The integration of natural cycles into construction scheduling required sophisticated understanding of both mathematical planning and practical logistics. The workforce requirements for the pyramid project have been estimated using mathematical models that consider the various tasks involved in construction. Recent research suggests that the peak workforce may have numbered between 10,000 and 20,000 people, including skilled craftsmen, general laborers, and support personnel. The mathematical distribution of workers among different tasks, quarrying, transport, stone shaping, and placement had to be carefully balanced to maintain efficient progress without creating resource conflicts. The mathematical achievement represented by the Great Pyramid's construction extends far beyond the monument itself. The organizational systems, planning techniques, and quality control methods developed for this project established precedents that influenced construction practices throughout the ancient world. The mathematical principles applied to solve the pyramid's construction challenges provided tools and techniques that would be adapted for other ambitious building projects across different civilizations. Modern computer simulations have enabled researchers to test various theories about pyramid construction methods using sophisticated mathematical models. These analyses can explore how different approaches to transportation, lifting, and placement would have affected construction timelines, workforce requirements, and material usage. The mathematical insights gained from these simulations continue to refine our understanding of ancient construction capabilities and the remarkable achievement that the pyramid represents. The Great Pyramid stands as testament to mathematical knowledge applied on a scale that challenges modern comprehension. Every aspect of its construction, from the quarrying of individual stones to the coordination of massive work crews, required mathematical solutions to problems of extraordinary complexity. The successful completion of this project demonstrates not just the mathematical sophistication of ancient Egyptian civilization, but also their remarkable ability to translate abstract mathematical knowledge into physical reality on a monumental scale. As we prepare to explore the mathematical principles that governed the precise angles and measurements that give the pyramid its distinctive appearance, we carry with us an appreciation for the extraordinary logistical achievement that made the monument possible. The transition from moving millions of stones to achieving perfect mathematical angles in their placement represents yet another dimension of the mathematical mastery that the pyramid's builders demonstrated throughout this remarkable construction project. In the gentle light of dawn, as shadows retreat from the Great Pyramid's eastern face, the monument's most defining characteristic becomes clear: the precise angle at which its faces rise toward the sky. This slope angle of approximately 51.84 degrees represents far more than an arbitrary architectural choice. It embodies mathematical relationships that governed not only this pyramid's construction, but the entire tradition of pyramid building that would span centuries of Egyptian civilization. The mathematical significance of this particular angle becomes apparent when we examine how Egyptian architects and builders conceptualized and measured slope. Rather than thinking in terms of degrees, as modern mathematicians do, the ancient Egyptians developed their own system for expressing angular relationships called the seked. This ingenious measurement expressed slope as the horizontal distance corresponding to each cubit of vertical rise, creating a practical tool that builders could use directly in their construction work without requiring complex trigonometric calculations. For the Great Pyramid, the seked equals 5 1/4 palms per cubit of height, a ratio that translates to the modern slope angle of 51.84 degrees. This seked measurement provided Egyptian builders with a concrete, measurable way to maintain consistent angles across the enormous faces of their pyramid. A master builder could instruct his workers to ensure that for every cubit the stones rose vertically, they should extend 5 1/4 palms horizontally, creating a standard that could be applied and verified at every level of construction. The mathematical elegance of the seked system lay in its direct relationship to the practical work of construction. Unlike abstract angular measurements, the seked could be verified using the same measuring rods and ropes that builders used for all their other dimensional work. This integration of angular measurement with linear measurement systems demonstrates the sophisticated mathematical thinking that characterized Egyptian architectural practice. The choice of 5 1/4 palms per cubit for the Great Pyramid sect was not arbitrary, but reflected deep mathematical considerations that connected the pyramid's geometry to fundamental numerical relationships. This particular seked creates a slope that produces remarkable mathematical properties in the pyramid's overall proportions. The relationship between the pyramid's height and the distance from its center to the midpoint of any base side forms a ratio of approximately 14:11, a proportion that appears throughout Egyptian architecture and may have held special mathematical or religious significance. The mathematical precision required to maintain this seked angle across the pyramid's 4 massive faces challenges modern understanding of ancient construction capabilities. Each face of the pyramid covers an area of approximately 26,000 square meters, rising over 140 meters from base to apex. Maintaining the correct slope angle across such vast surfaces, using individual stone blocks weighing tons each, required mathematical techniques that could detect and correct small deviations before they accumulated into larger errors. The process of translating the abstract seked measurement into practical construction guidance required sophisticated mathematical understanding of 3-dimensional geometry. Workers shaping stones for the pyramid's faces had to understand how the overall slope angle affected the specific cuts required for blocks of different sizes and positions. A rectangular block intended for the pyramid's face needed to be shaped so that its outer surface matched the slope angle, while its inner surface remained level to bond properly with the blocks below. Consider the mathematical complexity involved in cutting cornerstones, where 2 faces of the pyramid meet at a precise 90-degree angle. These blocks required compound cuts that maintained the correct seked angle on both faces simultaneously, while ensuring that the corner edge remained perfectly vertical. The geometric calculations required for such cuts demonstrate mathematical sophistication that rivals modern stone-cutting practices. The mathematical verification of slope angles during construction relied on techniques that combined the second measurement system with practical geometry. Master builders used devices called boning rods, long straight poles that could be positioned to check whether stone courses maintained the correct slope relationship. By sighting along these rods from various positions, builders could detect deviations from the intended angle and make corrections before they affected subsequent courses. The remarkable accuracy achieved in maintaining the pyramid's slope angles continues to amaze modern surveyors and engineers. Measurements of the Great Pyramid's faces show that the slope angles vary by less than 2 arc minutes from perfect consistency, representing a precision of better than 1 part in 1,000. This level of accuracy, maintained across surfaces covering acres of stone, demonstrates mathematical control of construction processes that challenges even modern capabilities. The mathematical relationships created by the pyramid's slope angle extend beyond simple geometric considerations to encompass sophisticated understanding of structural engineering principles. The 51.84-degree angle represents an optimal balance between several competing mathematical factors, maximizing the pyramid's impressive height while maintaining structural stability, creating pleasing proportional relationships while using materials efficiently, and embodying symbolic or religious meanings while meeting practical construction requirements. The structural mathematics of pyramid slope involves understanding how angular relationships affect load distribution throughout the massive stone structure. Too steep an angle would concentrate excessive weight on the pyramid's edges, potentially causing structural failure. Too shallow an angle would create a monument lacking the impressive vertical presence that proclaimed pharaonic power across the landscape. The chosen angle represents a mathematical optimum that satisfies both structural and aesthetic requirements. The mathematical analysis of pyramid slope angles has revealed that the Great Pyramid's angle produces several remarkable numerical relationships. The ratio of the pyramid's perimeter to its height closely approximates 2 times pi, suggesting that the builders understood sophisticated mathematical relationships between circular and rectilinear geometry. The slope angle also creates relationships between the pyramid's dimensions that echo mathematical constants and proportions found throughout Egyptian architecture. The consistency of slope angles across the entire pyramid required mathematical planning that extended from the foundational design through every stage of construction. The ancient architects had to understand how maintaining the correct seat at each level would ultimately produce the desired apex height and overall proportions. This required mathematical thinking that could visualize the completed structure while making decisions about individual stone courses during construction. The mathematical techniques used to establish and maintain slope angles influenced pyramid construction throughout Egyptian history. Later pyramids often employed similar sect measurements, though variations in these angular relationships produced monuments with distinctly different proportional characteristics. The mathematical analysis of these variations has provided insights into the evolution of Egyptian architectural thinking and the transmission of mathematical knowledge across generations of builders. The precision of the Great Pyramid's slope angles becomes even more remarkable when we consider the environmental factors that could have affected angular measurements during construction. Temperature variations caused measuring devices to expand and contract, potentially introducing errors into slope calculations. Wind could deflect plumb lines and other angle measuring instruments. The mathematical techniques employed had to account for these environmental variables while maintaining the exacting angular standards that the project demanded. The mathematical verification of the pyramid's angular precision has benefited from modern surveying techniques that can measure slope angles with unprecedented accuracy. Laser measurements and electronic surveying instruments have confirmed that the ancient builders achieved angular precision that approaches the limits of what can be measured reliably even today. This remarkable achievement demonstrates not just mathematical knowledge, but extraordinary skill in applying that knowledge under challenging construction conditions. The relationship between the pyramid's slope angle and its internal architecture reveals additional layers of mathematical sophistication. The passages and chambers within the pyramid display angular relationships that complement the external slope while serving specific architectural and possibly astronomical functions. The descending passage, for example, slopes downward at exactly 26 degrees, half the pyramid's face angle, creating a mathematical relationship that may have held symbolic significance for the ancient builders. The Grand Gallery, that soaring passage leading to the king's chamber, rises at the same 26-degree angle as the descending passage but in the opposite direction. This mathematical symmetry in the pyramid's internal angles demonstrates the systematic thinking that governed every aspect of the monument's design. The angular relationships within the pyramid create a three-dimensional geometric system that reflects sophisticated mathematical understanding of spatial relationships. The mathematical analysis of pyramid angles has extended beyond the Great Pyramid itself to encompass the entire Giza complex and other pyramid sites throughout Egypt. Researchers have discovered that the angular relationships established at Giza influenced pyramid construction for centuries, creating a mathematical tradition that maintained remarkable consistency across different reigns and construction periods. This consistency suggests that mathematical knowledge about optimal pyramid angles was preserved and transmitted through institutional memory that spanned generations. The astronomical implications of the pyramid's slope angle have provided another avenue for mathematical investigation. Some researchers have proposed that the 51.84-degree angle relates to astronomical observations that were important to ancient Egyptian religious beliefs. The mathematical analysis of these proposed relationships continues to generate debate among scholars, highlighting the complex interplay between mathematical precision and symbolic meaning in ancient architecture. Modern computer modeling has enabled detailed mathematical analysis of how the pyramid's slope angle affects its structural behavior under various loading conditions. These simulations can test the mathematical optimization achieved by the ancient builders, examining whether their chosen angle truly represents the optimal balance between competing structural and aesthetic requirements. The results consistently confirm the mathematical sophistication of the ancient design decisions. The Great Pyramid's slope angle stands as testament to mathematical knowledge applied with extraordinary precision and consistency across a construction project of unprecedented scale. The Seeked measurement system, the geometric techniques for maintaining angular accuracy, and the structural understanding that informed angular choices all demonstrate mathematical thinking of remarkable sophistication. The 51.84-degree angle that defines the pyramid's silhouette represents not just an architectural choice, but a mathematical achievement that continues to inspire wonder and respect, nearly 5 millennia after its creation. As we prepare to explore how this mathematical precision in angular relationships connected the pyramid to astronomical observations and cosmic alignments, we carry with us an appreciation for the extraordinary mathematical control that the ancient builders exercised over every aspect of their monument's geometry. The transition from earthbound angular precision to celestial mathematical relationships represents yet another dimension of the mathematical mastery that makes the Great Pyramid one of history's most remarkable achievements in applied mathematics. Under the vast canopy of stars that illuminated ancient Egypt, the Great Pyramid rose as more than just a monument to royal power or architectural ambition. Its builders conceived it as a mathematical bridge between earth and sky, encoding astronomical relationships in stone that connected their pharaoh's eternal journey to the cosmic cycles governing all existence. The pyramid's orientation, its internal passages, and its geometric proportions all reflect sophisticated mathematical understanding of celestial mechanics that transformed abstract astronomical knowledge into permanent architectural form. The most immediately apparent astronomical relationship lies in the pyramid's cardinal orientation, achieved with mathematical precision that continues to astound modern astronomers. The monument's four faces align with true north, south, east, and west to within 3 arc minutes of perfect accuracy, representing angular precision equivalent to pointing across 50 kilometers and being off by less than the width of a human hair. This extraordinary accuracy could not have been achieved through casual observation or approximate methods, but required sophisticated mathematical techniques that combined astronomical observation with geometric calculation. The mathematical foundation for this precise orientation lay in ancient Egyptian understanding of stellar motion and the geometric relationships that govern celestial observations. Egyptian astronomers had discovered that certain stars, particularly those in the circumpolar region that never set below the horizon, could provide reliable reference points for establishing true directions. By carefully observing the extreme positions of these stars in their circular paths around the celestial pole, ancient mathematicians could determine true north with remarkable precision. The technique most likely employed by the pyramid builders involved what modern astronomers call the simultaneous transit method. This sophisticated procedure required observing a circumpolar star at two specific moments, when it reached its highest point above the northern horizon and when it reached its lowest point during the same night. The mathematical principle underlying this method recognizes that true north lies exactly halfway between these two extreme positions, creating a geometric relationship that can be calculated with extraordinary precision. Picture the patience and mathematical skill required to execute this astronomical surveying technique. Night after night, the master astronomer would observe the selected star through a precisely constructed sighting device, carefully noting its position relative to artificial horizon markers. The mathematical calculations required to process these observations and translate them into terrestrial reference directions demanded understanding of spherical geometry and trigonometric relationships that reveal the sophisticated astronomical knowledge possessed by ancient Egyptian mathematicians. The choice of specific stars for these observations reflected deep astronomical knowledge that had been accumulated over centuries of careful observation. The ancient Egyptians likely used stars in the Big Dipper constellation, particularly those that maintain consistent brightness and follow predictable paths around the celestial pole. The mathematical analysis of star positions required understanding not only their apparent motion, but also the subtle effects of atmospheric refraction and other factors that could influence observational accuracy. The internal architecture of the Great Pyramid reveals even more sophisticated astronomical mathematics in the form of narrow shafts that extend from the King's Chamber and Queen's Chamber toward the pyramid's exterior surfaces. These shafts, long mysterious to archaeologists, appear to have been designed as astronomical observation channels that aligned with specific stars or star groups that held special significance in ancient Egyptian religious and mathematical thinking. The southern shaft from the King's Chamber points toward the constellation Orion, specifically the star Alnitak in Orion's belt, which the ancient Egyptians associated with Osiris, the god of the afterlife and rebirth. The mathematical precision of this alignment is remarkable. The shaft's angle of approximately 45 degrees was calculated to point directly at this star as it appeared in the southern sky during the pyramid's construction period around 2560 BC. The northern shaft from the King's Chamber aligns with what ancient astronomers called the imperishable stars, the circumpolar stars that never disappeared below the horizon and therefore symbolized eternal life. The mathematical angle of this shaft, approximately 32 degrees, was precisely calculated to target the pole star of the pyramid building era, which was not Polaris as it is today, but a star called Thuban in the constellation Draco. The mathematical sophistication required to calculate these shaft alignments demonstrates astronomical knowledge that encompasses several complex factors. The builders had to understand the effects of precession, that slow wobble of the Earth's axis that causes the positions of stars to shift gradually over centuries. They also had to account for the specific latitude of the Giza site and calculate how stellar positions would appear from that precise geographical location. The Queen's Chamber shafts display equally sophisticated astronomical mathematics, though their targets remain more controversial among researchers. The southern shaft appears to align with Sirius, the brightest star in the night sky, which the ancient Egyptians called Sopdet and associated with the goddess Isis. The mathematical precision of this alignment reflects understanding of the star's annual cycle and its relationship to the Nile's flood seasons, demonstrating how astronomical mathematics was integrated with practical calendar calculations. The northern shaft from the Queen's Chamber may have targeted stars in the Little Dipper constellation, though the exact stellar target remains debated among astronomers and Egyptologists. The mathematical analysis of this alignment requires sophisticated understanding of how stellar positions have changed since the pyramid's construction, involving calculations that account for thousands of years of stellar motion and precession effects. The controversial Orion correlation theory, proposed by researchers studying the Giza pyramid complex, suggests mathematical relationships between the positions of the three main pyramids and the stars of Orion's belt. According to this theory, the ancient builders deliberately positioned the pyramids to mirror the arrangement of the three belt stars, creating a terrestrial map of this celestially significant constellation. The mathematical analysis of this proposed correlation involves precise measurements of both pyramid positions and stellar coordinates, accounting for the effects of precession to determine how Orion's belt appeared in ancient times. Supporters of the theory point to statistical correlations between pyramid and star positions that seem too precise to be coincidental, while critics argue that the correlations fall within ranges that could result from chance or selective interpretation of the data. The debate over the Orion correlation highlights the challenges inherent in proving astronomical intentions in ancient architecture. The mathematical tools available to modern researchers can calculate stellar positions with extraordinary precision for any historical period, but determining whether ancient builders intended specific stellar correlations requires evidence that goes beyond pure mathematical coincidence. The mathematical relationship between pyramid dimensions and astronomical cycles provides another avenue for exploring the monument's celestial connections. Some researchers have proposed that the pyramid's proportions encode mathematical relationships to the solar year, the lunar month, or the cycle of precession itself. These theories suggest that the ancient builders used their monument as a kind of mathematical calendar or astronomical calculator, preserving important cyclical relationships in permanent stone form. The most plausible of these mathematical relationships involves the pyramid's base perimeter and its potential connection to the Earth's polar circumference. When measured in ancient Egyptian cubits, the pyramid's perimeter yields a number that, when scaled appropriately, approximates the Earth's polar circumference. This relationship, if intentional, would demonstrate astronomical and geographical knowledge that challenges conventional understanding of ancient scientific capabilities. The mathematical analysis of such relationships requires careful attention to the specific cubit standards used in the pyramid's construction and the precision with which these measurements were executed. Small variations in assumed cubit lengths can dramatically affect the mathematical relationships that emerge from dimensional analysis, highlighting the importance of accurate metrological knowledge in astronomical interpretation. The seasonal behavior of shadows cast by the pyramid provides additional evidence for astronomical mathematical thinking in its design. During the spring and autumn equinoxes, when day and night are of equal length worldwide, the pyramid exhibits peculiar shadow phenomena that suggest deliberate mathematical planning. The pyramid's shadow appears to have a slight concavity on its southern face during these equinoxes, creating an effect that has been interpreted as demonstrating the builder's sophisticated understanding of solar geometry. The mathematical explanation for this equinox shadow effect involves the pyramid's precise orientation and the subtle concavity of its faces. Each face is slightly indented toward the center, creating 8 triangular surfaces rather than 4 flat faces. This architectural detail, invisible from ground level but detectable through precise surveying, affects how shadows fall on the pyramid during specific solar conditions, creating the equinox phenomena that continue to fascinate observers today. The calculation of these shadow effects requires mathematical understanding of how the sun's apparent motion interacts with 3-dimensional architectural forms. The ancient builders would have needed to understand not only the geometry of their pyramid, but also the mathematical relationships governing solar position throughout the year. The precision with which they achieved these effects suggests astronomical mathematical knowledge of remarkable sophistication. The mathematical legacy of the pyramid's astronomical alignments extends far beyond the monument itself to influence our understanding of ancient scientific capabilities. The precision achieved in stellar alignments and solar relationships demonstrates mathematical thinking that bridges practical construction problems with abstract astronomical knowledge. The ancient builders successfully translated their understanding of celestial mechanics into architectural form, creating a monument that embodies mathematical relationships spanning from earthbound geometry to cosmic cycles. Modern computer simulations have enabled researchers to test various theories about the pyramid's astronomical mathematics with unprecedented precision. These analyses can recreate the night sky as it appeared during the pyramid's construction period, calculating exact stellar positions and testing proposed alignments against the physical evidence preserved in the monument's architecture. The results of these mathematical analyses consistently confirm that the pyramid's builders possessed astronomical knowledge of extraordinary sophistication. Whether or not all proposed stellar correlations prove valid, the monument clearly demonstrates mathematical understanding that encompasses accurate stellar observation, precise geometric calculation, and sophisticated architectural planning. The integration of astronomical mathematics into the pyramid's design reflects the holistic worldview that characterized ancient Egyptian civilization. For the pyramid's builders, mathematics was not an abstract intellectual exercise, but a practical tool for understanding and harmonizing with the cosmic order that governed all existence. Their monument stands as testament to mathematical thinking that unified earthbound construction challenges with celestial observation and religious symbolism. As we prepare to explore how modern mathematical techniques continue to reveal new secrets hidden within the pyramid's ancient stones, we carry with us an appreciation for the remarkable astronomical mathematics that guided its creation. The transition from ancient celestial knowledge to modern technological investigation represents a continuity of mathematical curiosity that spans millennia, demonstrating how mathematical truth transcends the boundaries of time and culture. In the quiet depths of the Great Pyramid, invisible to human eyes yet measurable through the mathematical precision of modern physics, cosmic particles called muons rain down from space, penetrating solid stone with the regularity of a celestial clock. These ethereal messengers from the upper atmosphere carry with them the power to reveal secrets that have remained hidden for over 4 millennia, secrets that even the most careful mathematical analysis of the pyramid's exterior dimensions could never uncover. Through the marriage of ancient stone and cutting-edge mathematics, we are witnessing the discovery of hidden chambers that may revolutionize our understanding of the pyramid's internal architecture. The mathematical principles underlying muon tomography represent one of the most elegant applications of particle physics to archaeological investigation. Muons, created when cosmic rays collide with atoms in the Earth's upper atmosphere, shower down upon our planet at a rate of approximately 10,000 particles per square meter every minute. These subatomic particles possess the remarkable ability to penetrate solid matter, passing through hundreds of meters of stone while losing energy in mathematically predictable ways. The mathematical foundation of muon tomography rests on the statistical analysis of how these particles behave as they encounter different densities of matter. When muons pass through solid stone, they lose energy at a rate that depends on the density and composition of the material they traverse. Empty spaces, such as previously unknown chambers or passages, allow muons to pass through with much less energy loss, creating detectable variations in the particle flux that can be measured and analyzed using sophisticated mathematical algorithms. Picture the extraordinary mathematical challenge involved in detecting these subtle variations in muon flux within the Great Pyramid's massive stone structure. The pyramid contains approximately 2.6 million cubic meters of limestone, creating a detection environment where the signal from a hidden chamber might represent only a fraction of a percent difference in muon intensity. Identifying such small variations requires mathematical techniques that can distinguish genuine signals from the random fluctuations that characterize any measurement involving particle detection. The mathematical processing of muon tomography data involves complex algorithms borrowed from medical imaging and adapted for archaeological applications. Just as computed tomography scans use mathematical reconstruction techniques to create three-dimensional images of the human body from two-dimensional X-ray projections, muon tomography employs similar mathematical principles to reconstruct the internal structure of massive stone monuments from measurements of cosmic ray particle flux. The discovery of what researchers have termed the Big Void within the Great Pyramid represents a triumph of mathematical analysis applied to particle physics data. This previously unknown space, located above the Grand Gallery and possessing a volume comparable to that of the Grand Gallery itself, was detected through careful mathematical analysis of muon flux variations measured over several months of continuous observation. The mathematical confirmation of this hidden chamber required sophisticated statistical analysis that could distinguish between genuine structural voids and the random variations inherent in particle detection. The research teams employed multiple independent measurement techniques using different types of muon detectors positioned at various locations around and within the pyramid. The mathematical correlation between these independent measurements provided the statistical confidence necessary to announce the discovery of a previously unknown architectural feature. The implications of this discovery extend far beyond the simple identification of empty space within the pyramid. The mathematical analysis of the big void's position, orientation, and dimensions provides new data that can be used to test and refine theories about the pyramid's construction methods, internal architecture, and the mathematical principles that guided its design. The void's location suggests architectural planning that may have involved mathematical considerations not previously recognized by researchers. Modern computational fluid dynamics has enabled mathematical analysis of air circulation patterns within the pyramid that could explain the function of newly discovered voids and the long-known internal chambers. These mathematical models simulate how air would flow through the pyramid's internal passages under various temperature and pressure conditions, providing insights into the environmental mathematics that may have influenced the design of internal spaces. The mathematical modeling of thermal effects within the pyramid has revealed how temperature variations could create air currents that might have served specific functions in ancient Egyptian religious or practical applications. The pyramid's massive stone structure acts as a thermal reservoir that moderates temperature fluctuations, creating internal environmental conditions that can be analyzed using mathematical heat transfer equations derived from modern engineering science. Ground-penetrating radar surveys have applied electromagnetic mathematical principles to probe the pyramid's internal structure from different angles and with different resolution capabilities. The mathematical processing of radar signals involves analyzing how electromagnetic waves reflect from interfaces between materials of different electrical properties, creating subsurface maps that complement the findings from muon tomography and other investigation techniques. The mathematical combination of data from multiple investigation techniques has enabled researchers to create increasingly sophisticated three-dimensional models of the pyramid's internal architecture. These computational models integrate measurements from muon tomography, ground-penetrating radar, thermal imaging, and traditional architectural surveys, using mathematical optimization algorithms to reconcile sometimes conflicting data sources into coherent structural models. Digital photogrammetry has enabled mathematical reconstruction of the pyramid's external geometry with unprecedented precision, creating detailed three-dimensional models that can be analyzed using computational techniques impossible with traditional measurement methods. These mathematical models provide baseline data for testing various theories about the pyramid's proportional relationships, construction sequence, and architectural planning principles. The application of machine learning algorithms to pyramid research represents a cutting-edge mathematical approach that can identify patterns in complex data sets that might escape human analysis. These artificial intelligence techniques can process vast amounts of measurement data, looking for mathematical relationships or anomalies that might indicate previously unrecognized structural features or construction techniques. Mathematical stress analysis using finite element modeling has enabled engineers to test how the pyramid structure responds to various loading conditions, including the effects of internal voids on overall structural stability. These computational analyses can evaluate whether newly discovered chambers create structural vulnerabilities or whether they were designed as integral parts of a mathematical load distribution system that enhances the monument's stability. The mathematical reconstruction of the pyramid's construction sequence has benefited from computational modeling that can simulate different building scenarios and test their feasibility against known constraints. These models can evaluate the mathematical logistics of various construction theories, analyzing workforce requirements, material transport schedules, and construction timelines with precision that was impossible using traditional analytical methods. Laser scanning technology has enabled mathematical documentation of the pyramid's geometry with millimeter-level precision, creating digital archives that preserve detailed measurements for future mathematical analysis. These high-resolution datasets provide the foundation for computational studies that can detect subtle geometric relationships or construction details that might have been overlooked in previous investigations. The mathematical analysis of construction tolerances throughout the pyramid has been revolutionized by the availability of precise digital measurement data. Researchers can now calculate how construction errors accumulated across the monument's massive structure, analyzing whether apparent imperfections represent limits of ancient construction capabilities or deliberate design features that served specific mathematical or functional purposes. Computational archaeology has emerged as a new field that applies mathematical modeling techniques to understand ancient construction processes and architectural planning. These mathematical approaches can simulate how ancient builders might have approached complex construction challenges, testing whether proposed building techniques could have produced the mathematical precision observed in the finished monument. The mathematical optimization of construction scenarios has enabled researchers to evaluate the efficiency of different building strategies, analyzing factors such as workforce utilization, material transport costs, and construction timelines. These computational analyses provide quantitative frameworks for comparing different theories about pyramid construction methods and identifying approaches that would have been most mathematically efficient given ancient technological constraints. Virtual reality reconstructions based on mathematical modeling allow researchers and the public to experience the pyramid's architecture in ways that were impossible before the development of advanced computational techniques. These immersive mathematical environments can visualize proposed chamber layouts, construction sequences, and architectural features with precision that brings ancient mathematical thinking to life in digital form. The integration of satellite imagery with mathematical analysis has enabled researchers to study the pyramid within its broader geographical and archaeological context. These computational approaches can analyze how the pyramid relates to other structures in the Giza complex, examining mathematical relationships in site planning that might have influenced the monument's design and orientation. Mathematical network analysis has been applied to study the relationships between different chambers and passages within the pyramid, treating the internal architecture as a complex mathematical graph that can be analyzed using algorithms derived from computer science and operations research. These approaches can identify architectural patterns that might not be apparent through traditional geometric analysis. The mathematical preservation of pyramid data through digital archiving ensures that future researchers will have access to increasingly comprehensive measurement data sets for continued analysis. These digital repositories enable collaborative mathematical research that transcends geographical boundaries, allowing scholars worldwide to contribute to our understanding of the pyramid's mathematical significance. The mathematical legacy of modern pyramid research extends beyond archaeology to influence developments in particle physics, computer science, and engineering. The techniques developed for analyzing muon tomography data have applications in nuclear waste monitoring, geological surveys, and security screening. The mathematical algorithms created for processing pyramid measurement data contribute to broader advances in computational imaging and three-dimensional reconstruction. As mathematical techniques continue to evolve, new possibilities emerge for understanding the pyramid's architecture and construction. Quantum sensors, advanced artificial intelligence, and improved computational modeling promise even more sophisticated mathematical analysis of this ancient monument. The marriage of cutting-edge mathematics with ancient stone continues to yield discoveries that bridge the mathematical achievements of past and present. The Great Pyramid stands as testament to the enduring power of mathematical investigation to reveal truth across millennia. From the ancient mathematicians who encoded sophisticated knowledge in its proportions to the modern researchers who use advanced computational techniques to decode its secrets, the monument represents a continuous tradition of mathematical inquiry that spans thousands of years. Each new mathematical technique applied to its study adds another layer to our understanding of both ancient achievements and the mathematical principles that govern architectural excellence. As we prepare to reflect on the complete mathematical legacy of the pyramid and its builders, we carry with us an appreciation for how mathematical investigation transcends the boundaries of time and technology. The computational techniques revealing new chambers today operate according to the same fundamental mathematical principles that guided the pyramid's original construction, demonstrating the timeless nature of mathematical truth and its power to connect human understanding across the centuries. As the first light of dawn touches the apex of the Great Pyramid, illuminating limestone blocks that have witnessed over 170,000 sunrises, we find ourselves standing at the intersection of mathematics and eternity. This monument, conceived in numbers and built through mathematical precision, represents perhaps humanity's most enduring testament to the power of mathematical thinking to transform abstract knowledge into permanent reality. The journey we have taken through Egyptian mathematics, from hieroglyphic numerals to cosmic alignments, reveals not just the story of an ancient construction project, but the profound relationship between mathematical understanding and human achievement. The mathematical legacy of the Great Pyramid begins with the elegant simplicity of Egyptian numerals, those visual symbols that made abstract quantities concrete and comprehensible. From the single stroke representing 1 to the raised arms figure symbolizing 1 million, the Egyptian number system provided the foundation for mathematical thinking that would enable architectural achievements of breathtaking scope and precision. The additive nature of their notation, where larger numbers emerged through combinations of basic symbols, reflects a mathematical philosophy that built complexity from simple, understandable elements. This mathematical approach, where sophisticated results emerged from the careful combination of basic principles, characterized every aspect of pyramid construction. The unit fractions that seemed so limiting to modern mathematical sensibilities actually demonstrated profound insight into numerical relationships. Egyptian mathematicians understood that any fraction, no matter how complex, could be expressed as combinations of simple unit fractions, revealing mathematical truths about the fundamental nature of numerical relationships that modern mathematicians continue to study and admire. The practical geometry that emerged from the annual flooding of the Nile created mathematical tools that would prove essential for monumental construction. The rope stretchers who re-established field boundaries after each flood developed geometric techniques that could maintain precision across vast distances and irregular terrain. Their understanding of similar triangles, right-angle construction, and area calculation provided the mathematical foundation for architectural projects that would challenge the limits of human organizational capability. The mathematical sophistication revealed in papyri like the Rind mathematical papyrus and the Moscow mathematical papyrus demonstrates thinking that bridged practical problem-solving with abstract mathematical exploration. Egyptian mathematicians could calculate the volume of truncated pyramids using formulas that would not be formally proven until much later in mathematical history. They approximated the value of pi with accuracy sufficient for any practical application. They solved problems involving unknown quantities using techniques that presaged later algebraic thinking. The translation of this mathematical knowledge into the Great Pyramid's design reveals minds capable of extraordinary conceptual thinking. The 14:11 slope ratio that defines the pyramid's silhouette was not chosen arbitrarily, but reflects deep consideration of mathematical relationships that connect the monument's geometry to fundamental constants like pi and possibly the golden ratio. The pyramid's proportions encode mathematical truths in stone, creating a monument that serves as both architectural achievement and mathematical theorem. The astronomical mathematics embedded in the pyramid's orientation and internal architecture demonstrates understanding that encompassed celestial mechanics, terrestrial geometry, and religious symbolism. The precision with which the monument aligns with cardinal directions, achieved through sophisticated stellar observation techniques, required mathematical knowledge that combined spherical astronomy with practical surveying. The internal shafts that target specific stars reflect calculations that accounted for precession, latitude effects, and the three-dimensional geometry of the pyramid structure. The construction mathematics that governed the pyramid's realization represents organizational thinking on a scale that challenges modern comprehension. Coordinating the quarrying, transport, and placement of 2.3 million stone blocks required mathematical planning that encompassed logistics, quality control, and resource management across a construction timeline spanning decades. The precision achieved in maintaining geometric relationships throughout this massive construction effort demonstrates mathematical control of building processes that rivals modern capabilities. The mathematical analysis of construction techniques, from the geometry of ramp systems to the mechanics of stone lifting, reveals ingenious solutions to engineering challenges that combined practical understanding with theoretical knowledge. Whether the builders employed straight ramps, spiral ramps, or internal lifting systems, their approach required mathematical optimization of multiple competing factors, including structural stability, construction efficiency, and geometric precision. The saked measurement system that governed the pyramid's slope angles exemplifies the practical mathematical thinking that characterized Egyptian engineering. By expressing angular relationships in terms of horizontal distance per unit of vertical rise, Egyptian builders created a measurement system that could be applied directly in construction without requiring complex trigonometric calculations. This integration of mathematical abstraction with practical application demonstrates the mature mathematical culture that supported Egyptian architectural achievements. The remarkable precision achieved in the pyramid's construction, from the squareness of its base to the consistency of its slope angles, required mathematical techniques for error detection and correction that operated at tolerances measured in millimeters across structures covering acres. The mathematical discipline necessary to maintain such precision throughout a construction project of unprecedented scale speaks to organizational and technical capabilities that challenge our assumptions about ancient mathematical knowledge. The modern mathematical techniques that continue to reveal new secrets within the pyramid demonstrate the timeless nature of mathematical inquiry. Muon tomography, computational modeling, and digital reconstruction all apply mathematical principles to decode information that the pyramid's builders encoded in stone 4.5 millennia ago. The mathematical algorithms that detected the Big Void operate according to the same fundamental principles of statistical analysis and geometric reconstruction that guided the pyramid's original design. The mathematical relationships that modern researchers continue to discover within the pyramid's architecture suggest layers of meaning and intention that may never be fully understood. Whether the builders consciously intended to encode specific mathematical constants or whether these relationships emerged from other design considerations, the monument clearly embodies mathematical thinking of extraordinary sophistication and depth. The mathematical legacy of the Great Pyramid extends far beyond the monument itself to influence the development of mathematical knowledge throughout human history. Greek mathematicians acknowledged their debt to Egyptian mathematical traditions, building upon foundations laid by temple scribes and royal architects. The geometric principles embodied in the pyramid influenced architectural traditions that spread throughout the ancient world and continue to inspire mathematical thinking today. The psychological and aesthetic impact of the pyramid's mathematical proportions demonstrates the deep connection between mathematical harmony and human perception. The monument's ability to inspire awe and wonder across cultural and historical boundaries may result partly from mathematical relationships that resonate with fundamental patterns in human cognition. The pyramid stands as evidence that mathematical beauty transcends the boundaries of culture, language, and time. The preservation of mathematical knowledge through institutional memory that spanned generations reveals the sophisticated educational and cultural systems that supported Egyptian mathematical achievements. The conservative tradition that maintained mathematical techniques across centuries ensured continuity of knowledge while allowing for gradual innovation and improvement. This balance between preservation and progress enabled mathematical understanding to accumulate over time, ultimately supporting architectural achievements of unprecedented ambition and precision. The integration of mathematical knowledge with religious and symbolic meaning in Egyptian culture created a holistic worldview where mathematical understanding served not just practical purposes but also spiritual and philosophical ones. The pyramid embodies this integration, serving simultaneously as royal tomb, religious symbol, architectural achievement, and mathematical demonstration. This multidimensional significance suggests mathematical thinking that encompassed the full range of human experience and aspiration. The mathematical investigation of the Great Pyramid continues to yield new insights into both ancient achievements and the fundamental nature of mathematical knowledge itself. Each new technique applied to the monument's study reveals additional layers of complexity and sophistication in its design and construction. The ongoing mathematical analysis of the pyramid demonstrates that mathematical truth transcends the limitations of any particular historical period or technological capability. As we stand in the pyramid's shadow, contemplating the mathematical journey that brought this monument into existence, we recognize in its limestone blocks not just ancient ambition or religious devotion, but the eternal human drive to understand, measure, and create. The numbers that guided its construction, from the simple unit fractions of Egyptian mathematics to the complex geometric relationships that define its proportions, represent mathematical thinking that bridges the practical and the transcendent. The Great Pyramid stands as humanity's most enduring mathematical achievement, a monument where abstract numerical knowledge became physical reality through the application of mathematical principles with unprecedented precision and scale. Its builders transformed the intangible realm of numbers into solid stone, creating a structure that embodies mathematical relationships in forms that will endure as long as human civilization itself. In the gentle light of dawn, as shadows retreat from the pyramid's eastern face and the monument prepares to begin another day in its mathematical dialogue with the cosmos, we are reminded that mathematical truth is not bound by time or circumstance. The same mathematical principles that guided ancient astronomers in their stellar observations, that enabled Egyptian engineers to achieve impossible precision, and that allowed master builders to transform mathematical concepts into architectural reality, continue to govern our universe today. The Great Pyramid represents more than an ancient wonder or archaeological curiosity. It stands as proof that mathematical knowledge, carefully developed and skillfully applied, can create achievements that transcend the limitations of any single generation or civilization. In its limestone blocks, precisely positioned according to mathematical principles that remain valid today, we see reflected the timeless power of human mathematical thinking to create meaning, beauty, and permanence in an ever-changing world. The numbers that live in stone at Giza continue to speak across the millennia, telling stories of mathematical achievement, human ingenuity, and the eternal quest to understand our place in the mathematical order that governs all existence. As long as humans seek to measure, calculate, and create, the Great Pyramid will stand as inspiration and testament to what becomes possible when mathematical knowledge is wedded to human determination and expressed through the patient accumulation of precisely placed stones, each one a small victory in the endless human quest to transform mathematical dreams into lasting reality.